Hello, and welcome to the Data Engineering Podcast, the show about modern data management. Introducing RudderStack Profiles. RudderStack Profiles takes the SAS guesswork and SQL gruntwork out of building complete customer profiles so you can quickly ship actionable, enriched data to every downstream team. You specify the customer traits, then Profiles runs the joins and computations for you to create complete customer profiles. Get all of the details and try the new product today at dataengineeringpodcast.com/RudderStack. Your host is Tobias Macey, and today I'm interviewing Razi Raziuddin about how data engineers can empower data scientists to develop and deploy better ML models through feature engineering. So, Razi, can you start by introducing yourself?
Absolutely. Thanks, first of all, Tobias, for having me on the podcast. Very excited to be here. I'm the CEO and co-founder of FeatureByte. We're a Boston-based startup focusing very much on scaling enterprise AI, primarily by radically simplifying feature engineering and management. I've been in the Boston area for now over 2 decades, data and analytics, bringing innovative data and analytics products to market. I've had the good fortune of being on the leadership team of 2 different unicorn startups. I was at DataRobot most recently, where I helped scale the company from just around 10 employees when I first joined to 850 employees in under 6 years, which was just an amazing ride. And prior to that, I was at another unicorn before the term was used for, describing interesting startups. I was at a company called Netezza, which is also Boston-based. Did an IPO and then was sold to IBM for close to $2 billion in 2010. So just being in the space has been fascinating. It's evolving every other day. There's just something new to learn. Just a very exciting space. So look forward to the conversation.
And do you remember how you first got started working in data?
So I moved to the Boston area with a company called EMC, which is now part of Dell. And that was in the data space. I was fascinated with data for one reason or the other, right from grad school. So I wanted to be in the data space. And then I really got hooked into analytics and data when I was at Netezza. I got the firsthand view of basically how data and analytics helps drive businesses, and saw the power of analytics and how it can be used to truly create a moat around businesses. Saw customers were just fascinated with the kinds of things that they were able to do with data. And then, moving into DataRobot, the power of ML was just truly amazing. It was just, again, just amazing to see what data analysts and business analysts were able to do with AutoML, or they were able to create just super interesting models by just uploading their data and clicking a few buttons here and there. And it's just, again, it's fascinating for me to be at this sort of convergence of business and technology, which is really where analytics lives. And then you look at the space, it's just, there's something new happening every other day. It's just so exciting. There's so much innovation. So you feel you learn something new literally every single day.
Absolutely. That's definitely how it's been with running this podcast and my other shows and just working in the space for the past, I think, decade plus at this point. Focusing in on the topic at hand for today, we're talking about feature engineering. And before we get too far into that, why don't we just start by giving a recap of what even is a feature and how is it distinct from a table in a warehouse or an ML model or any of the other data assets that we produce as data engineers?
No, absolutely, yeah. That's a great question. I think the best place to start is just the fact that great AI needs great data for it to be successful. Great AI starts with great data. And features are the data elements that get fed into algorithms to train machine learning models and to be able to do predictions off of these machine learning models. And so you can think of features as just elements of different entities. So they're attributes of different entities, good, Examples are demographic information associated with, for example, a customer or a product. So age, sex, gender, etc. Those are simple features that can just be derived from data that exists around a particular entity. But features can get super complex, and a lot of the features actually get derived from raw data. And so you can think of, for example, in the case of credit card fraud as an example, knowing that I'm sitting in Boston while my credit card is being swiped in, I don't know, Moscow or Timbuktu. That's a pretty good indication that there's some kind of fraudulent transaction happening. But that's not something that's intuitive to machines. And so the data that's available needs to be represented in a form that algorithms can easily learn from. So in this particular case, the example that I just quoted, a data scientist would have to kind of derive that feature by calculating the distance between where a credit card holder like myself is sitting and where the transaction is taking place. Now, the distance, which is now measured in, let's say, thousands of miles, helps the algorithm, helps the machine learning model understand something about that transaction, and the model is able to flag it as potentially fraudulent, right? This is, again, a pretty simple example. Features can get super complex, especially when you're trying to represent purchase behaviors and patterns. For example, are you a regular shopper or a binge shopper? Differences between shopping behaviors and patterns associated with a particular age or demographic. What are the kinds of things you like to buy? How consistent you are? How diverse the purchase patterns are? Those are the kinds of things that constitute features, and the more complex they are, the more signals they carry within them in order to, again, train models as well as be able to derive some really good predictions out of those models.
And so, in the process of developing a feature, the term feature engineering comes up a lot. And I'm wondering if you can talk through what that is, why it matters, who cares about feature engineering, and in what ways is it distinct from some of the other types of data engineering pipelines that folks might be familiar with.
No, absolutely. And so the process of basically taking raw data, which exists in data warehouses and data lakes, um, into these features, that process is feature engineering. So it's a critical part of the whole machine learning lifecycle, where you're transforming your data into your raw data into data that can be easily fed into machine learning algorithms for training and for predictions. So as far as how feature engineering and feature pipelines are different from traditional data pipelines, that's a topic that it all depends on how much time you have and how much time you can spend on talking about that. But happy to dive into it. I think one of the most common misconceptions especially in the data engineering world, is that a pipeline is a pipeline at the end of the day, right? It's just taking data from one place to another, doing some transformations. And when you think about features, they are transformations in some way. Conceptually, they're very similar to doing ETL type of transformations or ELT transforms. The challenge is, and this is something that just helps sort of get across the difference between traditional BI and analytics pipelines and machine learning pipelines. The fundamental difference is, BI is for humans and for human consumption, and AI is for machines, right? And so, that fundamental difference leads to all kinds of complexity in feature pipelines. So feature pipelines, when you dig underneath, they're at least an order of magnitude more complex, if not even more so, compared to your traditional BI and analytics pipelines. If you think about the scale, each machine learning model can easily utilize hundreds of features, whereas dashboards may have 5 to 10 metrics max, again, for more human consumption. When you look at the data volumes, typically your model training requires lots of detailed historical data, which means you're dealing and doing a lot of complex computations on literally large volumes of data, which makes data movement through these pipelines super expensive and inefficient. The computational complexity is much higher in features as opposed to calculating metrics. Metrics are typically simple statistical functions that involve, let's say, 2, 3, maybe 10 columns. Whereas when it comes to features, you could have many different tables, many different columns being joined together, and super complex computations in a time-aware manner being done. And so the time awareness, time travel, the need for consistency between training and serving, all of those things just make the ML pipelines and feature pipelines super complex and very difficult to sort of build, manage, govern, deploy, and just make sure they're healthy and operational.
In terms of the feature itself, it seems like it's distinct from the output of an ETL pipeline in that the ETL pipeline, once it's produced the output, that output is static until the next time the pipeline runs. Whereas the feature sounds like it's more actually the definition of a function that is used to compute the actual value at request time versus just loading something that has already been computed because of the fact of what you were saying of needing to be able to have this historical look back of what are the values over time. So a single feature is actually the function that's used to compute those values at whatever time span is being requested by the training operation.
No, absolutely. Yeah, I think that's again a super important point, Tobias, which is uh, you know you're constantly computing features as new data arrives. So there are jobs that are running in the background, basically computing features, making them available for predictions that typically require low latency, much lower latency compared to your BI report or a dashboard. And so that again increases the complexity of when data becomes available and when, how long it takes to actually compute the feature and make the results of the feature available for consumption by different applications out there.
And another term that comes up often in conversations where features or feature engineering are present is the idea of a feature store or a feature platform. I'm wondering if you can talk through your views on the necessity of a feature store in relation to the computation and delivery of features, and what are the trade offs for having that be its own dedicated architectural or infrastructure component.
No, absolutely. Yeah. I think from my perspective, feature stores are absolutely critical component of the machine learning architecture. You need the ability to deploy pipelines consistently and quickly. That is something that feature stores make available. Um, the also the need to serve features at low latency, that's also something that is a critical element of what feature stores deliver for machine learning pipelines and architectures. I think that it's really interesting you bring up the point around whether feature stores need to be a separate component or a separate infrastructure altogether versus being integrated into the modern data stack. Um, for us, the if you look at traditionally, given the complexity of the compute as well as the scale requirements, you pretty much had to go off and build a feature store that was completely separate and a dedicated infrastructure to deal with the processing and serving requirements for features. But this ends up creating all kinds of challenges. You now have to manage, build and manage a completely separate infrastructure, which means additional cost and separate teams that are dedicated to managing this infrastructure. Data privacy and governance just becomes a huge concern. Features are, they carry lots and lots of signals associated with highly sensitive data. and not being able to manage that in an environment where the rest of the data is managed is just becomes hugely challenging. And then, if you have a separate platform, a separate environment for processing data, it just leads to data inconsistency as well. Because data that's landing in your data warehouse may be slightly different from, when it gets pulled into a completely different environment. So from our perspective, if you look at, what the modern data stack looks like, and the power, that's just available in modern cloud platforms like the Snowflakes and the Databricks and BigQueries of the world. There's just so much compute power available now, especially with the separation of compute and storage. And plus the kinds of capabilities that are being built into these platforms just makes it very easy to run super complex computations on massive data sets. So it just makes sense now to build feature stores in the data platform itself. Just push the compute to where the data lives instead of having to move the data into a completely separate environment. It just automatically leads to better governance, better utilization of infrastructure that already exists. Just mitigate some of the privacy concerns, increases consistency of the data. And there are obviously going to be certain situations where the current data platforms, they just don't have the ability to just do low latency serving, as an example, or acting as a really good cache, or being able to process embeddings from NLP and LLMs very efficiently. In those cases, you just extend the modern data stack instead of building a completely separate infrastructure. That's kind of our view, at least for what customers should be thinking of building.
Digging more into the special case of feature engineering as compared to ETL workflows, I'm wondering if you can just talk through what is the overall life cycle of a feature, going from the ideation of what it should be through to the definition to deployment and maintenance.
No, absolutely. Yeah, this is this is something that, I'll talk about the life cycle of the features, and also touch upon where things are kind of broken from our perspective. So the life cycle itself is, you create features, you run experiments on the features, so you build models to understand which features are the most interesting given a particular use case and the type of model you're trying to create. And then you serve those features for training, as well as primarily for predictions, and then manage and govern the features, monitor the health of the pipeline. So if you just sort of dig into each one of those, the process of just coming up with the right features, that requires a lot of domain knowledge and deep understanding of the data. And it requires a lot of data science and coding skills to extract the right signals from the data itself, right? So just to create the features, you need to have the data scientists and domain experts and SMEs sort of working together. And then when it comes to experimentation, it's about creating a very accurate view of historical data to train models, the process that's known as backfilling. And then being able to train the models themselves to understand which features are important. Thankfully, when it comes to training models, there's all kinds of tools available, auto ML tools out there that just make it very, very easy for even non-data scientists or citizen data scientists to go off and build models very efficiently. One of the key areas of challenge comes up when you're trying to sort of serve build data pipelines to serve features for inferencing or for predictions. That's where you need a lot of help from data engineers to build machine learning pipelines. And that interaction between the data scientists and data engineers is fraught with friction. It just slows down the entire process. We've seen many situations where it literally takes weeks, if not months, to go from when the features are even created and the experimentation done to actually deploy features in production. And that just it's been one of those things where we see that as a major sort of stumbling block in being able to truly scale enterprise AI. And then finally, you've got management and governance. This is becoming increasingly important even for non-regulated industries, where it's important to know sort of who touched what data, who has access to which data, ensuring that the health of feature pipelines as data is constantly changing, as well as being able to manage the cost associated with the number of features just exploding in different environments, and ultimately governing which features actually get deployed, where they get used, and by who. All of that needs to be sort of centrally managed and governed as far as possible. So that's the life cycle of features and sort of some of the challenges associated with the life cycle.
In terms of the sharp edges or roadblocks that manifest in that overall life cycle, what are the biggest pain points that you see teams running up against, and what is the role of the data engineer in addressing those, maintaining those, enabling other members of the team and other participants in that process to get their work done without having to ask the data engineer for permission or to do a particular step every time they need to get something done?
Yeah, I think you're pointing to an area that, as I was mentioning, is just truly fraught with friction in some ways. Um, One of the key challenges with this whole life cycle is it requires three different skills. You need the domain knowledge, you need data science expertise, you need data engineering expertise to come together. You need domain knowledge to be able to determine, okay, what signals to extract from the data itself. You need data science knowledge to extract those signals, and then ultimately data engineering expertise to be able to perform all of these operations at scale. And the challenge is, these skills tend to live in different teams within a given organization. They use different tools, they speak different languages, they don't necessarily understand each other. And so you can, just um, pretty much see where the points of friction are, right? It's when, you have three completely different teams trying to interact with each other, it just makes that entire process super complex. And then, honing in on the interaction between data scientists and data engineers, that it just is a huge problem in of itself. Even though both these personas work on data, the way they approach problem solving and the way they approach the data itself is just vastly different. It's almost like the old Mars and Venus book, where data engineers, or take your pick, data engineers are from Mars and data scientists from Venus, or the other way around. But the fact of the matter is that data scientists are experimenters, right? They work on open-ended problems. They like to continually iterate on data, run a bunch of experiments. Whereas data engineers they're builders. They work on well-defined specifications to build pipelines that are healthy, they're easily maintainable, and they do what they're supposed to do. They're the opposite of experimenters. And so when these two personas come together, it obviously creates a huge friction to get things done. And then when we look at this space out there, there's a dearth of tools to make data scientists a lot more self-reliant when it comes to data, and when it comes to doing using and preparing data for modeling, and for data engineers to be able to create just these ML ready pipelines, incorporating some of the key requirements such as time awareness, low latency serving, etc. And I think it just exacerbates the challenge and the friction in the whole process.
For data engineers who are working in a team where data scientists or ML engineers are going to be the primary definers and maintainers of features, what are the interfaces that they're going to be looking to use to more closely integrate that process into their workflow and their tool chain.
Yeah, that makes sense. I think for for us, just looking at it from a perspective of the data scientists, I mean, ultimately, data scientists are the ones who come up with features. They're the ones who are using these features for building models, and they're ultimately responsible for the overall predictive power and the health of the models, and by association, the health of the features that get built. And so, from my perspective, data scientists are the ones who should ultimately be responsible for the entire feature lifecycle. And data engineers or ML engineers should be there in a support function to create the right environment and create the right architecture that makes it easy for data scientists to consume data, build pipelines, deploy, do the entire lifecycle in a self-service manner. Right? And so when it comes to the interfaces, if we sort of double click on this and look at each of the 4 steps I described in the feature lifecycle, it'll be interesting to dive into that and sort of look at what those interfaces would actually mean. When it comes to feature creation, it's, as I was mentioning, it's super important for data scientists to understand the domain and the context behind the data. So some way of making it easy for data scientists to interact with domain experts and subject matter experts, and some way of sort of creating a common language so that the interaction becomes much easier is super important. Give you an example. When it comes to different signals and signal types associated with features, both data scientists as well as your domain experts understand RFM, recency, frequency, and monetary metrics, right? That is one way. So extending RFM into different dimensions, such as diversity of purchases, similarity of behavior, etc. Those are ways in which you can make the interaction between SMEs and data scientists a whole lot easier. The rise in popularity, for example, of semantic layers, that's primarily being driven by the need of having data professionals and subject matter experts and business professionals come together and have a common way of sort of interacting and speaking with each other. That again will help this entire process of interacting with the subject matter experts. The other challenge that we see over and over again is just having to write tons and tons of code for doing the same sort of things over and over again. All right, so it's instead of having to write tons of Python code to create features, it should just be a simple declarative language that makes it very easy to take even some of the more state-of-the-art functions that, for example, Kaggle grandmasters use to win Kaggle competitions, and just be able to use those and have the backend SQL or Spark auto generated, which will make the entire process of not just feature creation, but also the experimentation and pipelining a whole lot easier, right? So that's when it comes to feature creation itself. If we get to experimentation, there's a huge reliance on data engineers to give data scientists different cuts of data, different slices of data on which they can do their experiment in a silo. I think that process again is sort of fraught with challenges and risks. First, there's an obvious reliance on data engineering teams just to pull data from a data warehouse or data lake and dump it into a different environment. But also the fact that your experimentation is being done in a silo in a different environment, as opposed to where the model or the feature pipelines are ultimately going to get built. That just leads to potential errors and inconsistency in the data, right? And so, just having the ability to actually run your experiments on live data is super, super helpful for data scientists. It just shortens the time between coming up with ideas and actually running experiments, and being able to do that again in an environment where the feature pipelines are ultimately going to live. And then, for this, we see a lot of sort of reinvention of the wheel going on. So if there's a really powerful feature catalog that exists that makes it easy for data scientists to come in and not have to recode everything that's already been done, reuse what's already out there. That is just a super efficient way of sort of, and an interface that makes experimentation super easy. Moving on to serving, this is, as we were discussing earlier, this is one of the most painful parts where it's a very error prone and sort of time consuming cycle. And for 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 me, a lot of the challenges come from taking features that have been created in Python and translating them into time-aware SQL and Spark, right? And that process, there's no reason why that should be a manual process, right? That's with these LLMs and generative AIs being able to even understand language. We should just be able to very easily and simply take features that have been declared in Python and create the equivalent Spark or SQL that's appropriate for the right backend, and deploy those pipelines and have the jobs associated with those pipelines run in an automated fashion, right? And ultimately, you need really good management, because these features they carry sensitive information. They're sort of super curated pieces of data that need to be managed very effectively and efficiently. And ultimately, any good self-service environment just needs to have the right oversight in order for smooth functioning, and being able to run the right way. And so having giving the ability for the organization to sort of centrally manage and govern and monitor the health of the pipelines, the cost associated with these different features, giving them the ability to manage the privacy and sort of access controls around features and feature pipelines, that becomes super important as well. That, I think, sort of creating that environment will truly sort of, unleash the ability for data scientists to just do a whole lot more. It's one of those things that holds data scientists back when it comes to enterprise AI, and we feel like this is something that's just going to 10x the ability for data scientists to just go off and build more models, deploy them, manage and monitor, and keep updating them as there's new data that arrives, as there are changes that happen in the market and the market conditions themselves.
And in terms of the creation of these platforms to enable feature engineering, what are the foundational components that need to be in place before the engineering team can start to think about building out these higher levels? And in particular, I'm interested in the data discovery aspect for the ML engineers and data scientists who want to define features, being able to understand what are the pieces of information available to them for doing that exploration and experimentation.
Yeah, I think it's a really interesting question. I think just having obviously as good quality data as available is a very, very important prerequisite for doing any kind of analytics, whether it's your traditional BI or doing ML on the data itself. Now, I'll also caveat that by saying that no one has very good data, right? I don't know of any team out there that'll claim that their data is perfect or close to perfect. There are always issues with the data. And so, this is always a journey to get to better and better data and high quality data over time. But that's, that even with decent quality data, you can do a whole lot, and that's an important prerequisite. The same thing applies to sort of the understanding of the data. If you look at data dictionaries and the sort of data catalogs, there's just tons of information that's always missing. And when it comes to data science, the more the more variety of data that exists, the better it is for modeling and for ML purposes. The Again, it needs to be an iterative process where you start with the data that's fairly well understood. You build some models, and then you continue to run experiments with data that perhaps is not as well fleshed out, is not as well understood, just to work with the data SMEs and business SMEs and gain a better understanding. And it just becomes a cycle where over time the need from the business as well as from data science teams to have better quality, well-defined data ultimately drives the organization to sort of go in that direction.
Because of the fact that feature engineering is such a all-encompassing process where it requires quality data, it requires up-to-date information, it requires cooperation and collaboration across different stakeholders within the team or within the organization. What are the communication channels or collaboration utilities that are necessary to be able to, you can't say ensure success, but at least to help promote success in this overall effort?
Indeed, yeah, that's communication between these teams is definitely a huge challenge, and I think the if you look at what the current channels are for communication, it's all the usual ones like email and Slack and spreadsheets, on which different pieces of information get exchanged, the requirements get tracked and maintained, and while those are a good start, they're definitely not sufficient. They're good for informal communications, but when it comes to sort of formalizing the semantics as well as the requirements behind certain elements of the data, features, etc., you need something that's a lot more powerful. And so, this is where a feature platform that allows those communications to happen much more efficiently becomes a really an integral part of the overall ML lifecycle and pipeline. Um, this is not to say that everything will, necessarily should just live inside a feature platform. There will always be all kinds of informal communication that happen. But when it comes to formal sort of a contract, let's say between the subject matter expert or the data producer and the consumer, in this case, the data scientist teams, that needs to be much better formalized inside some kind of a feature tool or a platform.
For teams who are just starting on the journey of building out their ML systems or empowering their data engineer or empowering their data scientists or ML engineers to do this feature development, what are some of the early mistakes that you see them often running into where maybe they would be better served by just buying something off the shelf or using an open source tool? What are some of the not invented here syndrome cases that you see happen frequently?
Yeah, that is super interesting. We see that in a we've seen that actually in a lot of different places where either due to necessity or due to the inventiveness or the desire of data engineering teams, there have been interesting attempts at building out what I would call first generation uh, feature stores primarily, or feature repositories. And, in some ways, given the plethora of tools that exist, it's not that difficult to come up with infrastructure that allows you to, build these pipelines and, help do feature engineering effectively. The challenge becomes sort of dealing with the overall complexity and just the speed at which things keep changing in the overall environment, both with data as well as just the underlying technologies, right? And keeping up with both of those just becomes a huge challenge for data engineering teams. So we've seen a lot of places where these repositories get built, data scientists come in and start using it, and soon it goes from being a nice, well-governed piece of infrastructure to becoming what I would call a feature lake instead of feature store or a feature repository, where there, every data scientist comes in and dumps whatever that they've done, creates more noise and compute complexity in the overall process. And it's not that difficult to see when you talk to clients out there, feature stores with literally tens of thousands of features that have been created by teams of 20 to 25 data scientists. And you think, okay, well, how is that possible? Well, one of the key reasons is there's no governance. There's no cataloging of what's already been done. And so you end up with just a sort of explosion of features in your feature platform that just becomes almost impossible to maintain over time.
So on that point of maintenance, who is primarily responsible for ensuring that you don't end up in that situation of just having a morass of features where you have 5 different versions of a feature that almost do the same thing but not quite, and no clear way to determine which one is the one that's actually being used? What are some of the ways that teams need to be thinking about how to maintain that overall? Who is responsible for that process? What are some of the overarching analytics that are necessary to be able to understand when it's necessary and when it's possible to reap old features and just delete them out of the repository, etc.?
Yeah, I think that's a great question. I think it goes back to Tobias, the some sort of standardization in the way features actually get created. Because if you think about it, right, a data scientist that comes in, for them to even, sort of find and trust the features that have been created and deployed, if it takes longer for them to do that, to understand what's inside a feature versus having, just writing their own code, which they trust. Obviously, a good data scientist is going to lean towards the latter, which is, oh, okay, well, it takes me 2 days to figure out the code that's been written by my colleague. I'd rather just write my own and just deal with it. And so having a sort of declarative framework, a structured way, a low code way of creating these features, that just makes it super easy, first of all, to promote reuse of what already exists. And then you need a super strong catalog. And in many ways, we feel like catalog should be something that's self-organizing. It should just, automatically organize features based on, understanding what the lineage associated with the data is, the class of signal, for example, that it's, emanating based on the computation, perhaps the complexity of the computation. There are different ways of sort of organizing, categorizing these features, right? But doing that in a much more automated way is super important, because otherwise, you're always relying on data scientists, categorizing and labeling features and data that they produce, which is difficult to rely on. So that's step number one. And then, when it comes to overall governance, it's the responsibility of senior data scientists, perhaps the chief data scientist, or VP or director of data science, who has to impose some kind of sort of governance guardrails to ensure that this doesn't continually happen, where there are features that get created that are ungoverned, that may carry sensitive information, and make it available to the general public.
Yeah, the security and PII aspect was another thing I was going to ask about. So you beat me to the punch there. And the other thing I'm curious about, to your point of standardization, is whether there has been any convergence within the overall ecosystem on the standard set of interfaces, both for exposing information to these different feature platforms and feature stores as far as what data is available, how does it get consumed, where the query or exploration interfaces for being able to process that data through those features. And then on the consuming side for building the ML models, has there been any standardization in terms of how the model training or model development tools and platforms interface with those features to be able to query them as part of that training and model building process?
Yeah, I think a lot of the interfaces for, especially for modeling and for model building and predictions, those are fairly standardized, although there's no standard that exists, but there are not too many variations in the way that modeling tools and modeling platforms consume data. And so that's fairly easy to sort of standardize around. Uh, Creation of features is something that's been very ad hoc over time, and despite the availability of interesting Python packages, R packages, etc., um, that focus a lot more on the experimentation side, but not so much on actually deploying these feature pipelines. And so, now there's a resurgence of interest in being able to create declarative frameworks for, especially in Python, that just make it very easy for data scientists to go from declaring features in a few lines of code and 6 to 8 lines of code, and being able to create truly state-of-the-art features, and actually deploying those pipelines, being able to backfill, run experiments on, etc. So yeah, it's a space that's rapidly sort of emerging. In fact, FeatureByte, we just released a Python SDK not too long ago, just a few weeks ago, that addresses exactly that pain point of being able to create features very efficiently, very quickly, and then be able to deploy them in production as well.
From your experience of working in this space, building a tool chain around the development and serving and maintenance of features and working with teams who are going along that journey themselves, what are some of the most interesting or innovative or unexpected ways that you've seen those teams solving that problem, building their own feature platforms or leveraging existing feature platforms to power their work?
Yeah, I think that's it's interesting. I think most of what we've seen is what I was describing as sort of first generation feature repositories, more like feature lakes. And we've seen in organizations, literally with tens of thousands of features that just keep computed over and over again. One particular example that comes to mind is super interesting. It's there was a company where the feature store was actually built by a management consulting company, not an IT consulting company. Plus, it's one of the top management consulting companies that came in and built a feature store. And this is many years ago, and the same features are still being utilized now. So it's again, it shows that yeah, it's not just that it's hard to do, which is one of the reasons why data scientists tend not to spend too much time on sort of trying to get these features into deployment, but at the same time it's just so critical for businesses out there to do analytics the right way. There has to be a different way.
And another thing I was just realizing is that we've spent a lot of the conversation focused on the role of the data engineer in this context of feature engineering and collaboration with ML engineers and data scientists. But another thing that we touched on earlier was the disparity between business intelligence and more point in time analytics versus the continuous time analysis of machine learning models. I'm curious what you have seen as some of the ways that analytics and business intelligence teams collaborate with the ML teams to understand more about the problem domain, or ways that they can feed off of each other in the process of building ML models to support the business based on some of the acquired knowledge through that work of building the more point-in-time analytical interfaces?
Yeah, I think Tobias, that there are, there's still lots of commonality in, for example, the data quality, which affects ML pipelines a whole lot more than BI pipelines and BI metrics. So any changes or corrections that are done in the data that's being fed into feature pipelines, that automatically helps BI pipelines as well. When it comes to semantics, the need to have a deeper understanding of the data is much more critical for feature pipelines, but ultimately it helps BI pipelines and any kind of BI analytics that's being done as well. So anything that ultimately is important for ML, it is super helpful, I should say, for BI and traditional analytics as well. And when it comes down to it, there has to be a sort of clear correlation between features and metrics. If the way metrics are being computed is very different from how features get computed, that's going to lead to challenges down the road in terms of explainability of models, the trust from the business on the data that's generating certain predictions. And so at the end of the day, the space has to converge when it comes to data management overall. But that's probably going to take a long while for something like that to happen.
And in your experience of building FeatureByte and working in this space of feature engineering and ML model development, what are some of the most interesting or unexpected or challenging lessons that you've learned in the process?
I think the one of the key things, this is true even when my co-founder and I were at DataRobot. It's true even now. It's just how model centric the world of AI is, right? And if you look at the number of tools that are out there for building models, doing hyperparameter tuning, experimentation, ML ops tools, etc. The whole space has evolved so much to help data scientists build and deploy really good models, right? But when you look at the first half of the ML lifecycle, which is everything to do with data and data management, there's a serious dearth of tools out there, right? It's you've got some labeling tools, data labeling tools. You've got some obviously you've got cloud data platforms that provide a lot of computational horsepower, but nothing that makes the overall process really straightforward, simple, and very scalable. And it just feels so lopsided. It's just been the case. When you look at the data side of the equation, it's literally what it was perhaps back in 2015. So over the last almost a decade, not much has truly changed and evolved, right? So it's something that from my opinion is ripe for disruption and ripe for major innovation in the space.
For people who are interested in digging more into the concepts around feature engineering, feature development, feature platforms, what are some of the resources that you have found most helpful in understanding and designing those capabilities?
Yeah, so for me personally, it's being looking at what some of the open source large companies that have open sourced some of their projects, what they've been able to do. So there are open source projects like Feast and others. Feather is one example coming from LinkedIn. They've done a really good job of sort of putting feature stores in the limelight, so to say, and being able to sort of express the criticality and the need for feature stores in the overall infrastructure. But outside of that, I look at the inspiration from Kaggle Grandmasters. We've got two of them on our team to understand the overall sort of power and criticality of feature engineering, how it's helped them, win amazing competitions, what they're able to do with the data, how they're able to derive some really powerful signals from the data. Talking to customers and understanding what their needs are, that's super important for us as we're building these capabilities out at FeatureByte itself. And then, believe it or not, just going through social media, especially on LinkedIn, and looking at data engineers voicing their frustrations about dealing with feature pipelines and ML pipelines, and the kinds of things that they have to, the machinations they have to go through in order to do things well. Those are just truly interesting inputs for us to consider as, or for any team to consider as they're building these capabilities out.
One other thing I was realizing I didn't touch on, and is maybe a conversation better suited for my other show about machine learning, is for this work of feature engineering, are there particular categories of model architectures or model types, so deep learning versus linear regression, et cetera, where feature engineering is more useful? In particular, I'm wondering if deep learning workflows really leverage feature engineering and feature capabilities versus just feeding it a whole bunch of data and hoping something useful comes out the other side.
Yeah, that's been, I think, topic of conversation again for at least a decade, if not more. And I'll give you an interesting anecdote. But to answer the question, feature engineering is something that's absolutely necessary for tabular data. Deep learning models don't do a really good job of building really good models with tabular data. There isn't a lot of it available in open source or in the open domain for deep learning models to learn from or chew on. Deep learning models just have a much larger appetite for data than what most enterprises kind of tend to have. And so, at least for now and for the foreseeable future, you need feature engineering to be able to sort of take raw data and create a representation of the real world for algorithms to be able to learn from and be able to do predictions on. And to your point, when it comes to deep learning and deep learning models, the you just feed in as much data as the algorithm can chew, and as much compute as is available to you, and interesting things tend to come out of that, as we've seen more recently. The anecdote that I was, going to share is I had the really good fortune of just having a quick chat with Jan LeCun at a breakfast in Boston, and I was asking him about feature engineering and what he thinks about this general space. And his comment was really interesting. He said, "Well, I've spent the last 2 decades of my professional career trying to get rid of feature engineering, but when it comes to tabular data, there's really no option out there." So yeah, I mean that's how the world is going to be, at least for now. And so, when even for companies who are thinking about, okay, well, do they need feature engineering, or especially with the Gen AI and LLMs out there, how should they be thinking about feature engineering for any kind of predictive problems? You ultimately need, especially predictive problems that involve tabular data, you need a combination of features and embeddings, potentially from unstructured data, textual data, NLP information that may exist. And you need to combine both of those in order to build really powerful machine learning models.
Are there any other aspects of the overall space of feature engineering, feature development, feature platforms that we didn't discuss yet that you would like to cover before we close out the show?
I think we touched upon quite a bit. So
All right. Well, for anybody who wants to get in touch with you and follow along with the work that you and your team are doing, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
Tobias, my response to that question is obviously going to be a little biased, but I'll try my best to put it in more general terms, right? Um, when you look at the modern data stack, you look at pretty much any image that represents all the different layers of the modern data stack, right? There are all kinds of interesting tooling available for traditional BI and analytics. So you have ELT that just makes ingestion super easy. You've got tools like dbt for transforming your data for analytics. You've got all kinds of interesting analytic and visualization tools. It all looks very neat and tidy and pretty well layered. One of the things that's missing is ML tools and platforms, right? I have rarely come across a picture or an image of the modern data stack that has the ML side of the equation well integrated into the overall map. And when you try to draw that out, the connection between the modern data stack, the cloud data platform, and your ML tooling is sort of very squiggly and a mess because it's all manually set up and managed. It's Wild West in some ways. Every organization does things very differently, and if for enterprises that are serious about scaling, that part of the equation just absolutely needs to change, and it has to change ASAP in many ways, right? I'll just go so far as to say that it's not having a self-service data platform for data scientists is one of the biggest hurdles in being able to scale enterprise AI, and it's something that's a badly needed extension to the modern data stack. So from my perspective, again, that's one of the biggest sort of data management challenges, or one of the widest data management challenges that I see out there that just needs to be fixed. And obviously, the modern data stack just allows the ability to do that very effectively.
All right. Well, thank you very much for taking the time today to join me and share your thoughts on the overall process and workflows and requirements for feature engineering and the capabilities that it enables. It's definitely a very interesting space. I appreciate all of the work that you and your team are putting into making that a bit more of a tractable problem. So thanks again for taking the time, and I hope you enjoy the rest of your day.
Thank you very much for having me, Tobias. Really appreciate it. The biggest sort of data management challenges, or one of the widest data management challenges that I see out there that just needs to be fixed. And obviously, the modern data stack just allows the ability to do that very effectively.
All right. Well, thank you very much for taking the time today to join me and share your thoughts on the overall process and workflows and requirements for feature engineering and the capabilities that it enables. It's definitely a very interesting space. I appreciate all of the work that you and your team are putting into making that a bit more of a tractable problem. So thanks again for taking the time, and I hope you enjoy the rest of your day.
Thank you very much for having me, Tobias. Really appreciate it.
Thank you for listening. Don't forget to check out our other shows, Podcast.init, which covers the Python language, its community, and the innovative ways it is being used, and the Machine Learning Podcast, which helps you go from idea to production with machine learning. Visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on Apple Podcasts and tell your friends and coworkers.